So let's start off with arc length. We actually talked about arc length on Wednesday a little bit, or today's Wednesday, on Monday a little bit. And that's, what is our definition of a radian? Or in other words, what is a definition? What does it mean to measure an angle in radians? And remember, what we said was that if I have an angle and we draw an arc centered about that angle, so a piece of a circle whose center is at the vertex of this angle, then how do I come up with the angle measurement in radians? Then it's actually a ratio of two quantities. It is the ratio of the arc length, this s, relative to the radius. Where our angle is in radians. So of course we can now use this formula and actually say then that our arc length is given by s is equal to the angle times the radius. And again, we always want the angles in radians. Let's emphasize that a bit. So basic example, if I say, let's give you certain quantities, let's see. So we have an angle measure. Of, let's say, pi over 3. And the radius is equal to 4. So pi over 3, about like that, 60 degrees. And our radius, 4 here. Then the arc length of this curve, we just multiply those two. So pi over 3 times 4, and that's going to equal 4 pi over 3. To keep track of units, remember, radians are a unitless number. The only number with the units here is 4. And let's say the radius is going to be measured in some sort of units, let's say inches. So that inches unit would carry on throughout the multiplication there, and the only units we're left with is that inches. And that's good measurement for arc length, for a distance. Okay, what about area now? Let's try to come up with the area formula and see if one of you guys can do it. By maybe writing down some examples of known areas. Primarily, what's the area of a circle? Anyone know?
Pi r squared.
Pi r squared, good. And the interior angle that we would travel if I go all the way around a circle is 2 pi. Always want to use radians. So if I have half of a circle, what's the area then going to be? It'll be half of that. But in this case, our angle is pi. And likewise, if I have a quarter of a circle, we will get 1/4 pi r squared, and the interior angle of pi over 2. Okay, well now what we want is just for an arbitrary angle. We have some piece of pi, we call these sectors. We'll have a radius, some interior angle measure of alpha. So what is my area formula then? Can anyone guess it? So we've got pi r squared, angle is 2 pi. 1/2 pi r squared, angle is pi. So the r squared's hanging out every single time. The angle, how does this constant relate to the angle?
It's usually half.
Half, exactly. So 1/2 times the angle times r squared is our area formula. And again, measured in radians. So for example, let's suppose we have an angle. I'm going to change the letters. Let's use theta for an angle. Let me say theta is 2 and the radius is 5. And we want to find the area. So that 2, there's no units on the 2. It's not a degrees, it's unitless. So it's radians. So that means this angle here, just 2 radians. I guess let's draw it to scale. How big is 2 radians? Anyone know? I think it's going to be second quadrant. So pi over 2, so it's going to be like 1.6-ish. So maybe 2 radians will be something like here. We've got 2 radians. We've got our arc. We've got our radius of 5. And we want to find the area. And we just plug those numbers in. Area is 1/2 times the angle, just 2, times 5 squared. So it looks like we'll get 25. Be careful with this formula. One of the common things that students want to do is just throw in extra pi's. So remember, if I just give you an angle of 2 radians is a good number. Don't throw in extra pi's into the formula. Okay, so that's it. Those are the 2 big formulas. Let's do some extra examples, see the types of problems you might see on test quizzes, web assigns, all that. We do a lot of these problems with ants walking around circles. Might get a little redundant, but I'm sure you'll see one. Not on this quiz, not on Friday's quiz, but on the big quiz coming up on Tuesday. And then maybe again next Friday after a week from this Friday. So we've got something like an ant travels around 200 degrees around a circle. Of radius 5. Let's give it units. Let's say 5 millimeters. Let's find the distance traveled. there 2 L's in traveled? I think there's only one. Actually, I think it doesn't matter. I think the more common is just one, but 2 isn't wrong. I'm going to say it's not wrong because I said so. Anyway, what's going on in this problem? We've got an angle and we've got a distance. The distance is a radius. What's special about the angle? Degrees. So another thing we can throw at you. We worked all on this on Monday, converting radians to degrees and vice versa. So make sure you guys practice that. First thing to do in any of these problems, make sure your angles are always in radians. So we've got 200 degrees times. We want to convert it, so I want to get rid of the degrees. Let's put the 180 in the denominator. Pi goes in the numerator. Pi radians to 180 degrees. The degrees units will cancel, and we are left with 20 over 18. So 10 over 9 times pi, or 10 pi over 9. That is just our angle. What do we want to find? Total distance traveled. So since it's staying on the edge of the circle, this is just going to be an arc length. So if we wanted to draw a picture, it's going to come around, go 200 degrees. So it's only going to stay on the outside though. Distance traveled is just going to be S. We've got our 5 millimeters for the radius. So our S, 10 pi over 9 times 5 millimeters. So 50 pi over 9 millimeters. Okay, let's do another example. So now suppose the ant starts in the center. Walks 3 inches to the edge. It's going to walk around the circle. And then back. The area that the ant carves out is 75 square inches. We want to know, how far did the ant walk? So he's going to start at the center. He's actually going to walk out 3 inches. He's going to walk around the circle some amount. We're not sure how far. Sorry, my circle is terrible. And the only thing we know is that the area, 75 inches squared. So how far did he walk? In this case, because he starts in the center, the total distance Well, he's walking 3 inches out. He's going to go around some distance according to the arc length. Then he's going to walk 3 inches back in. So we'll walk 6 inches walking out and back in, plus however far he walked around in the arc length. But how do we find our arc length? So we do know one fact about the area. Let's call the angle theta. And we know that the area is 75. And we know the radius was 3. So solving for this, multiply by the 2, divide by 9, we get 150 over 9 equals theta. And then simplifying that, let's go ahead and divide by 3, so we get 50/3. And if you check the units, we had inches squared here. 3 was a radius measured in inches, which would be inches squared. And when we divide that, we will get inches squared divided by inches squared. And both of those units cancel off. We are left with a unitless number. So that's a good radian measure. We needed this piece of information because arc length we need the angle. We know the radius. And now that we've used our other piece of information involving the area, we solved for our angle. And so now we can solve for our arc length. So 50/3 times 3. And so the arc length is just 50. Make sure we answer the full question. Our distance now is going to be 6 plus that 50. So total distance he walked is 56 inches. So again, 50/3 was unitless here. And that 3 was 3 inches from the radius. Okay, so let's do one more question. The last one we saw a little bit of work to do. We had to use this extra piece of information about the area to first then find the angle, then to find the arc length to answer the question. In this case, let's just give, I'm not going to have an ant or anything. Let's just suppose I give you the information of the arc length, 4 meters, and the area is 12 square meters. And I ask, what is the radius? Don't know the radius. We know that the arc length is 4 meters and that the area 12 square meters. We neither know the angle nor the radius. The question asks, what is the radius? So in this case, we're given sort of the end of these formulas, the end values that these formulas compute, the arc length, the radius, or excuse me, the arc length and area. And what we want to do is now reverse engineer the radius. This is essentially how all of these problems will go, is we have to give you two pieces of information. And from those two pieces of information, you can solve the rest. So both arc length and area, they depend on the angle and the radius. So if I know both of those, I plug them in, I can compute everything else. But now we're given sort of the opposite, arc length and area. And what we're going to do in terms of solving that, we're going to get multiple equations. We saw something similar like this last Friday when we were doing our COVID-19 example. So you will see this in exponential functions. If I am just given certain points on a graph, or I know an exponential function passes through specific values, if one of those values is not a nice starting value, we had to do some system of equations manipulation. Let's first write down what we have. Formulas are always a good thing to start with. S is equal to r theta, or theta r, and our area, 1/2 theta r squared. And we know arc length is 4, but that doesn't solve anything for us here. We have two unknowns still, the angle and the radius. And every time we have two unknowns, we need two equations. So if we plug in our 12 here for the area, we get something similar. Still an equation, but two unknowns in it. And so we want to use both of those facts to solve. How do we do that? We talked about dividing equations. You can add and subtract equations and scalar multiply them if you've done systems of linear equations. The other method is a substitution method. So you'll use this quite a bit in calculus, where we want to take one equation, solve for one of the variables, then plug that into the other equation. We'll start with the easier equation. Always makes things easier to solve for. And I'm actually going to specifically solve for theta. So why theta? Because I'm just kind of looking ahead a little bit. Theta in this equation is just theta. It's not theta squared, cubed, square roots, nothing fancy going on with that theta. Whereas the r, we would have to square it if I plug that in. And that could potentially be a source of errors. This one just makes it a little bit easier. I'm going to plug that guy in for theta, and we will get 12 is equal to 1/2 times 4 over r times r squared. One factor of r is going to cancel. And then 1/2 times 4 gives me 2. And so r is just 6. And if we want to check and keep track of our units, remember 12 is in meters squared. That 4, though, was a distance. So there was meters here. And r is measured in meters. So one of the r's cancel. This r was measured in meters. That 2 is measured in meters, which gives me a meter squared here, a meter squared here. And then when I divide by that 2, it'll cancel one of the meters. So we're left with just one factor of meters as our unit, which is what we need, right? We're just measuring a distance. Always encourage you guys to check units, keep track of them, especially because most of you, I imagine, are going to have to take some sort of bio, some sort of stats, some sort of physics or chemistry, where dimensional analysis is what we call it. Paying attention to your units is a good check to see if you did the problem right, if you ended up with the correct units. Any questions? Okay, so that's it for arc length and area. Just got to remember those formulas, get used to using them. I would definitely say I would encourage you guys to go back, take a look at the formula for arc length. Try to come up with some sort of mnemonic device, some sort of way of remembering it, or at least checking. We did this for the area of a sector and relating it to area of a circle. Hopefully you guys know. So you can always check like area, full circle, you plug in 2 pi for that angle, you should get our well-known formula for area of a circle. Okay, so let's jump into trig a little bit. We will introduce reference angles, sine and cosine. So when we're measuring angles, we are, let me try and draw a better circle here. Measuring them in standard position from a circle, but we also want to consider this overlaid with our Cartesian plane. So we consider the center of the circle right at the origin. And we have some angle. It's going to intersect the circle. Of course, one's along the x-axis, the other one somewhere else. And it's going to have some angle, theta. And what we're going to do now is start to construct functions where the independent variable is this angle. So far we've looked at y as depending on x. It's a little bit of x depending on y with talking about inverses. In this case, what we want to think of as, is there some sort of information we can get where essentially based on this circle, as we move around this circle, are there functions we can measure that depend only on the angle? And there's a lot of functions. We build these up. These are our trig functions. What happens with these angles and circles when we're drawing them in the plane, if we want to go back and forth in some senses, one measuring this angle and another thing talking about our coordinates, our xy coordinates, whatever point we intersect this circle at, xy, we can recover the x value. If I take this point and just project it down, then this distance is our x value. Likewise, if I project our point across, then the vertical distance is our y value. And so naturally, we start to see these right triangles show up when we're considering both rectilinear coordinates, xy coordinates, and angular information. So I'll label the radius there. So in this case, this gives us a triangle. Bottom side's x, vertical side's y, and the long side, the hypotenuse is always r at some fixed radius on a circle of radius r. And so the functions we're going to start off with are sine and cosine. The sine function, the sine of alpha, or theta, excuse me, measures the ratio of the opposite side to the hypotenuse of any right triangle with interior angle theta. In other words, in terms of the picture I just drew, we often like to write sine theta is opposite over hypotenuse, which is equal to y over r. So these trig functions start to naturally relate these Cartesian coordinates, our xy coordinates, with the sides of the circle and relate those back to the given angle that we're at. Likewise, our cosine function I'm just going to write adjacent to the hypotenuse. So cosine of theta, we often abbreviate it adjacent ADJ over the hypotenuse. And in terms of our diagram, it's going to compare that x value over r. And so to finish up, we've just got about 2 more questions on these guys. One, what happens if I change the size of the radius? A function needs to be well-defined. What does a well-defined mean? It means it has to fit the definition of a function, right? It can only have one output for any given input. And then our second question is going to ask, well, how do I compute these? Are there any angles that I can get nice enough mathematical expressions to actually find these ratios? So let's take a look. So let's say we have a smaller triangle and a bigger triangle. And again, we're going to have our coordinates overlaid. And we have this angle now. Might need a little more space. But when I draw these right triangles, according to these circles, they're going to have different values. Let's call it x1, y1, and r1 for that little inner triangle. And then the outer triangle, call it x2, y2, and the bigger radius, r2. And what we said was that sine of theta is y1 over r1. And the question is, does this equal y2 over r2? By our definition, it doesn't matter what size the triangle was, or what size the radius of the circle was. So why? Why doesn't it matter? Why should these two quantities be the same? Does anyone know? key thing is that we actually have similar triangles. So equal because of similar triangles. This is something that'll come up probably at least once this course. Come up probably at least once in calculus. In calculus, once you get in the related rates and word problems, you'll almost be thrown a little curveball with some similar triangles sometimes. And we often just kind of expect you to know some of these things and know how to work with similar triangles. What do similar triangles mean? Well, in similar triangles, the angles are all the same. So the smaller triangle has an angle of theta, an angle of 90, and then how many, what's the degree measure of a triangle is 180. So this upper angle has to be 90 minus alpha, 90 minus theta. Same thing for the bigger triangle. Both has an angle of theta, has an angle of 90, and then 90 minus theta. So the angles are all the same. They are just scaled differently on different sizes. And the thing about similar triangles is that the ratios of corresponding sides and the relative ratios of sides is always a fixed constant. So here the ratio of the opposite to the hypotenuse, the vertical side to the hypotenuse of the small triangle has to be the same as the ratio of the vertical side to the hypotenuse of the bigger triangle. So sine and cosine, well defined, doesn't matter the size of the triangle. And that's an important part because I like to use that fact to now answer our second question that we want to get to. Namely, how do I compute these? If I know specific angles, or are there specific sets of angles that we can compute nice enough mathematical expressions for in terms of sine and cosine? And then eventually we'll build that to the rest of the trig functions as well. So I want you guys to memorize these. I am not big on memorization. I do like to memorize as little as possible in any sort of math class because your memory can fail you, especially with formulas. You miss one constant. Let me redraw this one. So there's 45, 45, 90. In other words, pi over 4, and 90. And then 30, 60, 90. Pi over 6, pi over 3, pi over 2. And what are the ratios? We don't have to get the specifics of how big the triangle is. We just need the relative sizes. So pi over 4, 90. What you got to remember is 1, 1, square root of 2. The other one, you need to remember 1, 2, square root of 3. So when they're equal, 1, 1, 2, put the square root on the 2. When you have a triangle that's 30, 60, 90, remember 1, 2, 3, put the square root on the 3. 30, 60, 90, always remember short side is 1, long side is 2, long side is the hypotenuse, and then the other side, square root of 3. And that's all you have to remember in terms of triangles. I'll show you guys how to use this a bit more next week once we get into reference angles and reference triangles. The other thing I do want to say is I want to make sure you guys draw this to scale is another tip I would recommend. Common mistake is to flip these two angles to just label them wrong. If you don't draw this triangle to scale where one side's specifically shorter, a lot of students will get a little lazy and sometimes you'll draw almost a right triangle and you'll write pi over 6, pi over 3. But then because you don't have a visual reference of like which side's which, you can flip those two numbers and then end up computing the wrong values. So draw your triangles, 30, 60, 90 triangles to scale. One side short, one side a little bit bigger, and then the hypotenuse is the biggest. So that way you'll always remember Smaller angle, 30 degrees, pi over 6. Opposite the smallest angle is the smallest side. So 1, 2, square root of 3. All right. Any questions on anything?